Hi, my name is Rebecca Muller. Sometimes the functions that we come across in real life can be defined differently for different values of the independent variable. These functions are called piecewise-defined functions, and that's going to be the topic for today's lesson. Let's begin with an example. Let's consider the function f, which is defined as follows. F of x equals, and notice that there are three pieces to this definition. 3x plus 5 if x is less than or equal to 0. It's defined as 4 minus 2x if x is a value between 0 and 2, and defined as simply x if x is greater than or equal to 2. Let's see how to evaluate this for different values of the independent variable. First, let's begin with f of negative 5. Now, the function has three pieces, but the independent variable negative 5 is only going to be defined for one of the pieces. In this case, the first piece. F is defined as 3x plus 5 for any value of x less than or equal to 0. So we're going to evaluate f of negative 5 by substituting into 3x plus 5 for x. That gives us 3 times negative 5, which is negative 15, plus 5, and the value here is 10. We can also evaluate the function at the value of 0. Now, there's a 0 in both pieces, first and second, but notice that in the first piece, it's defined for x less than or equal to 0, whereas in the second piece, we have a strict inequality. The piece that we use to evaluate the function at 0 is going to be the first piece. That functional value will be 3 times 0, which is 0, plus 5 is 5. To evaluate f of 1, we look for the piece of the function where x is going to be in the correct interval. In this case, the value of 1 is in between 0 and 2, so we're going to use the second piece of the function. We've substituted in for x, and we evaluate 4 minus 2 times 1 to give us a value of 2. To find the functional value f of 2, we find the piece where x equals 2, and that ends up being in the third piece. Again, the strict inequality on the second piece disallows it. We evaluate the third piece by simply giving back the same value of x. And finally, evaluating f of 5 also takes us to the third piece of the graph, and we end up with the functional value of 5. Now, we're going to look at a new function and look at how we can graph such a function. Let's sketch by hand the graph of the following piecewise defined function. We're given the value of f equal to 2 plus x if x is less than negative 4. It equals negative x if x is between negative 4 and 5 inclusive. And it equals 3x if x is greater than 5. Notice that all three pieces are linear. Therefore, we're going to look at each piece individually, remembering the side conditions. We'll begin with y equals 2 plus x for x values less than negative 4. Now, even though x doesn't equal negative 4 in that piece, it is going to be an endpoint, a point of reference that we'll have to have. So we're going to substitute the value of negative 4 into the first piece and find out what the y value would be. 2 plus a negative 4 is negative 2. When we plot that point, these are unit values of 3 given on this graphic. We're going to plot negative 4, which is approximately here, and negative 2. Now, to plot it, we want to draw an open circle because it actually is not part of the graph, but it will be an endpoint that will be needed. When we substitute a second value into the first piece, we want to make sure we pick a value that's actually in that part of the domain. So we're going to substitute in, for instance, in this case, negative 5. Substituting in, we get 2 plus a negative 5 is negative 3. Plotting that point, negative 5, negative 3 is approximately here. And what we can now do is connect the dots, and we already determined this was linear, so we get a piece of the graph of that straight line. Now we're going to go to the second piece of the graph, y equals negative x. Notice that this piece is going to be graphed for values of x between negative 4 and positive 5. We'll substitute first for negative 4. When we take that value, we want the opposite of the x value, which gives us back positive 4. When we plot this point, negative 4, positive 4, notice that we're going to plot it as a solid point because it is included in that part of the domain. Next, we're going to go to the other endpoint, 5, and substitute in. Here we want the opposite of 5, negative 5. Plotting that point, we go 5 units over and 5 units down, and plot a second point. Again, it's a closed circle. And recall that what we want is just that segment of the line that connects those 2 points. Finally, we'll go to the third piece of the graph, y equals 3x. Here we want values of x greater than 5. Similarly to the first piece, we want to plot the point that gives us an endpoint, although we will graph it as an open circle. So we're going to substitute in the value of 5. That gives us back 15 as we multiply by 3. The point 5, 15, remember these are units of 3, 3, 6, 9, 12, 15, is around here, open circle, and I'll substitute in another value here. We'll substitute in 6 and evaluate to get 18, and if we go to 6, 18, we plot that point, and again, this is linear, so connecting the dots and extending that line. You can see that not only is the functional value algebraically given in pieces, but many times what happens graphically is you end up with different pieces for different parts of the function. Now, our graphing calculator will also support piecewise-defined functions, but we have to think a little bit about how to use this. We're going to use some rules for logic in order to be able to put this on the calculator. Let's do that now. Let's use a graphing calculator to graph the piecewise-defined function using the window indicated. Here our function is given as x cubed plus 5 if x is less than or equal to 0, and negative x squared if x is greater than 0. The window we'll use is negative 3 to 4 for my x values and negative 3 to 6 for the y values. Now let's transition over to the graphing calculator and see how we can graph that. On the y equals key, we're going to insert the first piece of the function under y sub 1. So I'll use parentheses and substitute in x cubed. I can get the cube off of my math function key, and plus 5. Now I'm going to close parentheses, and I'm going to use the logic that we discussed earlier. I'm going to use a division here by a logical statement. X, and I'm going to use the test function, is less than or equal to, that's number 6, 0. And I've inserted the first piece of the function. I'm going to insert the second piece of the function into y sub 2. That's negative x squared, in parentheses, divided by, and here we have x greater than, which is going to be number 3, greater than 0. Now, the way this works is, recall that on a logical statement, if the statement is true, it gives back a value of 1, whereas if the statement is false, it gives back a value of 0. So this is basically telling the calculator when to include something and when not to by giving back values of 1 and 0. I need to change my window to the window that was indicated. That's negative 3, 4. We'll keep the scale at 1. And negative 3, 6, again with the scale of 1. And now when we look at it graphically, there's the first piece of the graph, the x cubed piece, and then we see the x squared piece coming in as the second piece. Now there's an alternate method that we could use on the calculator, which I'm going to go ahead and show you, and that is to insert the entire piecewise-defined function in y sub 1. The way we would work it here is to insert the x cubed plus 5, and we're going to write it down. I can use a multiplication here, times x less than or equal to 0, close parentheses, and we put a plus sign, and then put the second piece in. So you could actually include all of the pieces of your function in one y equals just by putting plus signs in between each of the separate parts. Close parentheses. And again, we get the same graph. Now, one thing you'll notice here is that there are a few parts where it's trying to pick up some values next to the y-axis, which we didn't see when we graphed it separately. So it would be up to you as to whether you would like to see that vertical line or not. Another way to get around that is to use the connected mode, and we'll do that in our second example. Well, what I'd like you to do now is to try a problem on your own. I'm going to give you a function which is defined piecewise, and I'd like you to try to graph it first by hand and then to use the calculator. When we come back, we'll see how you've done on the problem by letting you see me work the problem and checking your work. Here's the problem. Graph the function first by hand and then with a calculator. The functional value f of x equals 4 minus x if x is less than 2, and 1 plus 2x if x is greater than or equal to 2. Now let's look and see if you were able to get the correct graph. We'll look at the graph by hand to begin with. Again, we've separated the two pieces of the function. Here I'm looking at the functional value y equals 4 minus x for values of x less than 2. We'll begin by plotting the endpoint, finding what happens when I substitute in the value of 2. And we have 4 minus 2 is giving me back the value of 2. We'll plot that as an open circle. Here my units are 1 unit each for each of the tick marks. So the point 2, 2 as an open circle. Now, to pick my second point to substitute in, I want to pick a value of x which is less than 2. I'll choose the value of 0, and substituting in gives us back 4 minus 0, which is 4. So plotting that point 0, 4 gives us a point on the y-axis. This is a linear function, so we're going to connect the dots, and we end up with our first piece graphed. Now let's consider the second piece, y equals 1 plus 2x. Here we want values of x greater than or equal to 2. We'll substitute in the value of 2 to begin with and evaluate. 1 plus 2x is 1 plus 2 times 2, gives us back the value of 5. And plotting the point 2, 5 as a closed circle, because it's included in the solution set. And then pick a value of x greater than 2, such as 3, and evaluate 1 plus 2 times 3, which is 7, and then plot the point 3, 7, and again linear, connecting the dots, gives us this graph. Now let's check and see whether you were able to do it on the calculator correctly. I'll go into my y values and clear out my y sub 1 and my y sub 1 and evaluate this. I'm going to use the method where we insert each piece separately into a y value. So y sub 1, I'm going to insert 4 minus x, close the parentheses, use the division sign, and put in the side condition x is less than 2. For y sub 2, we'll put in the second piece of the graph. That's 1 plus 2x, close parentheses, divided by, and here we want x to be greater than or equal to 2. Now, when we graph, I'm going to notice that this is the screen we had previously, doesn't give us a great picture. Let's go to the standard window and see what we get. And notice that we're ending up with the function as we had it by hand. One thing that the calculator won't be able to show you is whether the endpoints are actually included in this function or not. At least graphically, you cannot tell that. We want to give a rule of a function f defined piecewise for the graph shown. We also want to give the domain and the range. Notice we have two pieces for this function. The first piece is in the third quadrant, going to the point -1, -1. We can look at this piece of the function and look at it as a straight line with a slope of +1. Note from this point to the origin we go up 1 and over 1, and a y-intercept of 0 since it goes to the origin. And so that part of the function can be defined as f of x equals x, and here we want x to be less than or equal to 0. Because there's no open circle at the origin, we assume the point is included. The second piece that we're going to look at is a horizontal line. And so the y value for that horizontal line is a constant value of 2. And this will be true for x greater than 0. In our last example, we want to look at what is called the greatest integer function. It's a special piecewise-defined function. Let's look at its definition now. The greatest integer function is defined by using this notation. It's a double bar bracket. And we give the value of the greatest integer in the following manner. If we substitute in a value for x, which is an integer value, then the function gives us back that same value. If we substitute in a value of x, which is not an integer, then what we get back as our functional value is the greatest integer less than x. Let's see how to evaluate that in the following examples. Here we're looking at the greatest integer function, and we want to evaluate this first at -2. Well, -2 is an integer value, and therefore, by definition, the function gives us back that same value. Next, we want to consider f of -1.2. Since this value is not integral, what we want to do is to look at the value that is greater than the least value, right, less than that. Or in other words, what I'm trying to say is we want the value which is just less than that. So we're going to pick up again the value of -2, the greatest integer less than or equal to -1.2. Next we have the value 0.4. The greatest integer less than or equal to 0.4 is 0. Next, 1.8. The greatest integer less than 1.8 is 1. And f of 5, again, we have an integer value, so we can get back the value of 5. The last thing we're going to do is support these results by looking at the graph on the graphing calculator. To find your greatest integer function, we'll go to our y equals key. We're going to go under the math menu and then scroll over to number. Now, number 5 there, int, means greatest integer function. So we'll have greatest integer function of x. We're going to graph this, and you'll note that what happens is we have, looks like a step function, but you'll see these little lines between here. Actually, we should not be getting those lines back, but what's happening is that the mode that our calculator is in is what's called connected mode. If we change over to dot mode instead, then when we look at the graph, what happens is we get a nice little step function without the vertical lines inserted. Now, what we can do is then look at the table function and evaluate some of these same values that we were just looking at. I'm going to set the table so that we'll have an ask function. Let's go to table set and go down and make sure we're doing ask and go over to the table. And what I'm going to do is look at different different values of this function. For instance, let's substitute in -2 and we get back the value -2. Let's try -1.2 that we've done earlier, and again we get back the -2. And then recall we had the value of 0.4 and we're getting back the value of 0. And so on and so forth. We could continue with this in this manner. In conclusion, we want to think about piecewise defined functions because they turn up in a lot of applications that we have in daily life, such as mailing rates or the amount that you pay in a parking lot. You normally don't pay for the exact minute, you instead pay for a particular interval of time. Try some of these problems. You'll find plenty of exercises at the end of your section, and you can do some of those applications when you try.